So today we're going to talk a little bit about hemoglobin and specifically how oxygen and carbon dioxide bind to hemoglobin. So to start, let's look at what actually is hemoglobin. So hemoglobin is a component of red blood cells that efficiently carries oxygen from the lungs to the tissues and contributes to the transport of carbon dioxide and hydrogen ions back to the lungs. Hemoglobin is, as you can see, a quaternary structure. It is a tetramer, so it's got 4 different tiny subunits that you can see here and here, and it is composed of 2 alpha-beta dimers. So here you can see alpha-beta dimer 1 and alpha-beta dimer 2. So this is just the general structure of hemoglobin. So let's take a deeper dive and kind of see what it looks like on the molecular level. So we'll go to our next slide here. So hemoglobin contains heme, and that's this molecule here. Heme is a prosthetic group of hemoglobin. It is composed of an iron atom and an organic component called protopyrin, which is composed of 4 pyrite rings linked together by methine bridges to form a tetrapyral ring, as you can see here coming off of the iron atom here. And there are also 4-methyl, 2-vinyl, and 2 propionate molecules in here also, and this is what forms heme. And iron, as you can see, is at the center of the molecule, and under normal conditions, iron is in a ferrous oxidation state, where the iron ion has 2 more open bonds that it can form. And one of those bonds, or the 5th residue position as it's called, is bonded to a histidine residue referred to as the proximal histidine, which you can see here. And then the 6th bonding site, depending on whether it's deoxyhemoglobin or oxyhemoglobin, is where oxygen binds. So as you can see here in this illustration where you're looking from the side view of hemoglobin, we don't have anything bonded here, but we do have oxygen bonded here. And there's also another histidine residue on the opposite side of the heme molecule called the distal histidine, and the distal histidine prevents oxidation of the iron into a cation that can't bind with oxygen, and it also decreases the likelihood that carbon monoxide would bond to hemoglobin. As you can also see from this illustration, iron is such a large atom that it can't fit inside the porphyrin ring, so it's kind of hanging down here, as you can see. But when oxygen binds and the electrons and everything kind of get switched around, that iron actually becomes smaller and can fit in that plane, and it stabilizes the molecule. Well, the oxygen is stabilized in the molecule by binding, or oxygen by binding to the distal histidine. So kind of what does all of that mean in context of binding with oxygen? So hemoglobin is an example of an allosteric protein, and allosteric proteins often demonstrate the cooperative effect, where there is an increase of activity due to cooperation of subunits in an allosteric protein. As you can see here, hemoglobin, as compared to myoglobin, has more of a sigmoidal shape in its graph, so it's got that S shape. And this shows that there are 2 distinct interactions between all of the different binding sites within the hemoglobin. This interaction between the subunits allows for 98% of the oxygen binding sites to be occupied when hemoglobin is in the lungs, where the partial pressure of oxygen, or the PO2, is at 100 torr, as you can see here in this graph. And also, this allows for only 32% of binding sites to be occupied in the capillaries, where PO2 is only at 20 torr, as you can see here. And so when you look at the difference of that, that is 66%, and 66% of the potential sites release oxygen, which is significantly higher than that of myoglobin, which would only be 7%. And that's kind of why hemoglobin interacts in such a way that more oxygen can be released to the tissues that it needs to support a greater amount of cell function. So in summation, as oxygen pressures increase, affinity for oxygen binding by the hemoglobin increases. As you can also see, 66% seems kind of low compared to all of our cellular function in our body, but this is actually regulated by regulatory molecules, which we'll talk about later in the presentation. So we're going from the deoxygenated T state to the R state, or the oxygenated hemoglobin. So when oxygen binds to iron, or bonds to the hemoglobin, iron moves into the porphyrin plane, like we talked about earlier, that shifts upward, but that also shifts the proximal histidine with it. And that proximal histidine interacts with the carboxyl groups at the end of the alpha helix. And that's kind of in this interface where these subunits are interacting with each other. This interaction communicates with the other subunits so that the subunit rotates 15 degrees, as you can see here in this illustration where that molecule tends to shift just a little bit. This change to the interface communicates binding of oxygen to the other subunits, so it lets all the other subunits know that oxygen is bound, and that transition into the R state is all kind of done in synchrony. So back to the things that are regulating how much oxygen is actually binding to the hemoglobin. Hemoglobin binding with oxygen acts much like other allosteric proteins do with enzymes, in that they're regulated by regulatory molecules. 2,3-phosphoglycerate, or 2,3-BG, is an anionic regulatory molecule and occurs in equal amounts with hemoglobin and red blood cells. The anionic properties of 2,3-PG interact with positively charged groups on the beta subunits, and this kind of binds in a pocket present in the center of the tetramer. As you can see right here, that is where that 2,3-PG wedges itself, and that stabilizes deoxyhemoglobin, so it makes it a stable state so it doesn't want to go into that oxygenated state. This means that it reduces the affinity for oxygen to bind, and is why only 66% of potential oxygen is released total. So we can re-reference that graph here. And as you can see, if you purify hemoglobin, its oxygen carrying capacity is so much so that it would only release 8%. So what naturally occurs in red blood cells allows for 66% of that oxygen to be released for cellular use. And this ultimately, that 2,3-BPG would have to be released in order for oxygen to bind. So another thing that affects how oxygen binds to hemoglobin is pH. And the Bohr effect shows how pH affects how hemoglobin oxygen carrying capacity works. So much like 2,3-BPG, binding capacity, cells like those in the body, tissues, and capillaries where increased amounts of combustion is occurring and there's lower amounts of oxygen, more carbon dioxide is released. And when carbon dioxide is released from body tissues, it enters into red blood cells where it interacts with water, and to ultimately form carbonic acid and hydrogen ions, which ultimately lowers the pH. Oxygen loses its affinity to bind to hemoglobin at this low pH, releasing much needed oxygen to the cells that were releasing the CO2. So that's what's known as the Bohr effect. Under low pH conditions, histidine side chains in hemoglobin are stabilized by salt bridges, creating deoxyhemoglobin. This is also stabilized by forming carbamate with amino acid groups. So there's a lot of salt bridges being formed to kind of stabilize that deoxyhemoglobin state. And as you can see here, in the graph, as pH decreases, there's a greater release of oxygen. CO2, as you can see, also lowers oxygen carrying capacity, and it actually, in the presence of lower pH, can decrease it even more. So as you can see here in the graph, what would be 77% at pH of 7.2 is now 88% due to CO2 being present. And here is just another representation of that. As you can see, CO2 from cells undergoing combustion release the CO2, and then the CO2 interacts with water in red blood cells, and that's forming those hydrogen ions and the carbonic acid. And then some of that is released out into the cellular space, decreasing the pH. And then as this red blood cell is going back to the lungs, it's going to ultimately release that CO2, and then hemoglobin will pick up oxygenated, it'll be in it would be the oxygenated form of hemoglobin here, and it would repeat the cycle all over again. So in summary, as partial pressures of oxygen increase or decrease, depending on whether you're in the lungs or in the capillaries, oxygen affinity will increase when you're in the lungs and you have that greater PO2, and will decrease respectively in the capillaries. And as pH decreases, oxygen affinity decreases. And then in the presence of CO2, affinity for oxygen is then further decreased. And here's another little illustration of how that works in the body system. And here are my references. Thank you.